in the coming 15 to 20 minutes. The progress in materials can be intimately linked to the evolution of human civilization. You know, we talk about Stone Age, Bronze Age, Steel Age, Silicon Age, and now we are entering the Carbon Age. So, at every stage, the materials are either necessity driven or technology driven or sometimes curiosity driven. You know, these are the three ways in which new materials are coming into existence. And whenever you see a new material, it can be either evolutionary, it has evolved, or it can be revolutionary, where you really did not expect that this material has arrived. Okay. Now, there are varied criteria which are set for materials from aerospace to semiconductor devices. You know, for example, we need suitable materials for wind turbines, high-speed trains, fuel-efficient airplanes, batteries for mobile applications, catalysis for fuel cells, photovoltaics for solar cells, high-temperature alloys for boilers, nanomaterials for energy and environment, optoelectronic materials for night vision, and so on and so forth. All these are our family of materials. So, our buzzword today in the world of materials is better, stronger, lighter, durable, cheaper, and so on. So, we need easy to process, less environmental impact, amenable to non-ambient conditions, radiation, high pressure, high temperature, high magnetic field, etc. So, this area is truly multidisciplinary, interdisciplinary in the sense it has a strong link to fundamental science, physics, chemistry, classical metallurgy, and applied mathematics. So, the plan of my talk is the following. I'll first start with the role of computation in material science, and then I come to the simulation in different length scales. I'll talk about density functional theory. Some of you may be aware that there is a heterogeneous audience. Nevertheless, the youngsters, they should know what is density functional theory, which is a practical tool. And I'll take as a specific example, I cannot take many examples, I'll talk about graphene and graphene-inspired 2D nanostructure family. How to tune the electronic structure in the band gap. And finally, as Dr. Goswami also mentioned, how it is possible to couple computational database with machine learning. Okay, and then I'll continue. Now, the role of computer simulation in materials, it has already been a little bit talked about by Dr. Goswami. Now, traditionally, scientific and engineering paradigm is the following. We try to understand theory, whether it is classical or statistical or quantum. We try to understand theory and then perform experiments. However, the limitations are that there are sometimes difficulties, like we are unable to probe in desirable range. It is too expensive to carry out the experiment because of the sophistication and rare availability. Sometimes it is very slow, the waiting time is prohibitively long. Sometimes it is dangerous. For example, it can be toxic or radioactive. So, the computational science paradigm is the use of high performance computing to simulate the phenomena. So, as it has already been pointed out, apart from theory and experiment, the simulation is indeed coming as the so-called third pillar in material science. So, the computational resources are getting more and more powerful and economic, that is all well known, and the computational methods are becoming more accurate and versatile. So, these are the three things which are helping us in allowing computational material science to progress. Unprecedented growth of computer power. You know, when the first computer in 1944 during the Second World War, it was mega flop. And today, the computer which I am using in Japan, it's a K computer which is 10 petaflop. So, you see, number of zeros which has increased is by orders and orders of magnitude. There is a tremendous progress in parallel computing, cloud computing, and GPU computing, which I do not have to tell. Many people are aware of it, and it is all available in the literature. And last but not the least, there is a remarkable array of simulation techniques which are available today, covering a wide range of length and time scales, which you will see in the next slide. So, look at the length scales from angstrom to kilometer. Materials simulation requires a huge range. Time scale from 10 to the power minus 15 seconds to years. And we have got simulations in all these space. When you are in this particular length and time scale, you have got quantum simulations. When you go higher, you have got molecular dynamics or Monte Carlo classical simulation. Then you go to mesoscale, you do what is known as the coarse graining. Then you come to continuum model, which the materials engineers are interested, and finally you come to the plant or the macroscopic, the real lab. So this is what is a huge array of the hierarchy of models from nano to meso to micro to macro. Okay, and we have got the properties and parameters in the different regimes, and there is a quantitative structure property relationship which is there, and we are interested to know how it is possible to bridge the length scale from one to the other, and this bridging of the length scale, that is using the information extractable from one length scale as an input for the next length scale, that is the most desirable approach. Now the tasks and challenges in front of computational material science are the following: design, discover and synthesize new materials and molecular assemblies to atomic scale control. Probe and control photon, phonon, electron and ion interactions with matter. Perform multi-scale modeling that bridges the multiple length scale and time scale. Use the collective effort of condensed matter and materials. This is chemists, biologists, molecular engineers, and those skilled in applied mathematics and computer science. Multidisciplinary. And following are the considered to be the grand challenge in materials. This is for the youngsters. What are the grand challenges in front of us? Number one, how do we control material processes at the level of electrons? Number two, how do we design and perfect atom and energy efficient synthesis of revolutionary new forms of matter with tailored properties? How do remarkable properties of matter emerge from complex correlations of atomic and electronic constituents, and how can we control these properties? Number four, how can we master energy and information on the nanoscale to create new technologies with capabilities rivaling those of living things? Very difficult but very challenging. Finally, how do we characterize and control matter away, especially very far away from equilibrium under tremendously high pressure like geophysicists want? So the computational material science is definitely interdisciplinary, as you can appreciate. We require quantum mechanics, statistical physics, solid state physics, theoretical chemistry, molecular dynamics, Monte Carlo, bio-inspired simulations such as genetic algorithm, artificial neural network and so on, numerical methods and machine learning. There are several important landmarks and players who have all been, most of them have been given Nobel Prize. For example, density functional theory by Hohenberg, Kohn-Sham and Walter Kohn got the Nobel Prize in 1998. Multi-scale simulation method, I will come to that. Karplus, Weichel and Levitt, they did it in 1970s and they got Nobel Prize in 2013. And ab initio molecular dynamics, Rahman, Parinello and Carr in 1984, they got Dirac medal for this. Just if any of you are interested to know a kind of a bird's eye view, I wrote a review, first principles design of materials, and in this book review chapter in materials research, current scenario and future projections. This has been edited by R. Chidambaram and S. Banerjee, and if you want I can also send you the PDF version of it. So this is the Nobel Prize given to Walter Kohn in 1998 for the development of the so-called density functional theory, which is the most widely used method today for electronic structure calculations because of the approach which is proposed by Walter Kohn along with his co-workers Hohenberg and Sham. And recently we have celebrated a half a century because it was 1965 when this was introduced, and today we are 50 years ahead. Then came this multi-scale development, multi-scale models of complex systems by Karplus, Levitt and Weichel, and they worked together in Harvard in early 1970s, and then later on with Karplus and Weichel joined Levitt in Weizmann Institute, and they developed something which is really useful for macromolecules and biologically interesting systems. Then molecular dynamics. I particularly want to tell you about the fact that the father of molecular dynamics is Anisur Rahman, a person who was born in Hyderabad, and he is considered by the whole world to be, and today there is the Anisur Rahman Prize, which is the highest honor in the field of computational physics, which is given by the American Physical Society. Michele Parinello, a good friend of mine, is working in Switzerland now. Earlier he was in Max Planck Institute. He works under Anisur Rahman, and there is a Parinello Rahman molecular dynamics, which is most famous today. Later on with Roberto Carr in Italy, CISA, they developed what is known as the Carr-Parinello method, one of the most important things today for computational material science. Now, whatever little time is left for me, I'll just tell you something about the case studies in materials using DFT, and there are several happenings in materials science. It is not only happenings are there in high energy physics, you know, like the Large Hadron Collider, but there are happenings in material science, topological insulators, 2D materials, graphene and beyond, van der Waals heterostructures, and most recently the high throughput computational screening is giving rise to amazing things through combinatorial techniques and material informatics. So I don't want to tell you anything about the density functional theory excepting the fact that this is something which is a fantastic tool, and I would like to skip this because here the density is used as the basic variable, and the basic quantities that come out of it are charge density, spin density, total energy and force. This is the Hellman-Feynman force which molecular quantum mechanics tells us. And whole lot of properties emerge: electronic property, cohesive, structural, thermodynamic, chemical, optical, magnetic, transport, and even superconducting properties. Let's take an example of graphene, which all of you know was discovered about a decade ago, and there are a huge number of 2D materials which have come into existence today. Interestingly, the corresponding 3D counterparts were known by people for ages. Graphite people knew, today we talk about graphene. Silicon we knew, we talk about silicene. Like that, phosphorus we knew, today we talk about phosphorine. Cubic boron nitride, there are tons in metallurgy laboratories. Today we are talking about sheets of hexagonal boron nitride. Transition metal dichalcogenides were known to physicists for a long time. Today we have got layered transition metal dichalcogenides like molybdenum disulfide. So you see, from graphene to hexagonal boron nitride to molybdenum disulfide, they have got conductor to insulator to semiconductor, and they have got amazing properties such as one which is shown here. It is something which is a TV screen which is malleable. Okay, and more interestingly, there are sandwich structures of these which are called van der Waals heterostructures, which are giving to new functionality in devices. So the discovery of graphene has indeed marked the onset of a new and emerging paradigm in material science and device physics. Unfortunately, I do not have time to go into the details, but I'll just tell you DFT has been used for many applications, such as applications in energy materials. I recently wrote along with one of my students, an INSA monograph on science-based technologies for sustainable and adequate energy for India. Okay, those of you who are interested, you can go and see this INSA article. We also play with electron spin, and a new particular complete area is coming out, which is called spintronics. It is a growing. We have growing expectations for spintronics because we can now do electronic spin, polarize, transport, store, detect, and manipulate. I've written a recent article on spintronics, a revolution in material science and device physics in Physics News. Again, this is mostly for the students. Okay. So the current trend today is to go. This is the last part which I want to say. The current trend is to use high performance computing not only for the description and verification of results, but also for predicting new results, as Dr. Goswami also just very quickly pointed out. Okay. Now, descriptive simulation has elucidated many material properties, for example, structural, electronic, magnetic, optical, multiferroic, superconducting, etc. However, the parameter-free first principles calculations based on density functional theory has reached such an unprecedented level of accuracy, where it is not only managed to verify experimental results which we have done routinely, but also it allows prediction of advanced and functional materials and properties before even attempting to synthesize it in the laboratory. Remember that we have not yet performed the experiment, but we have predicted something that, look, this particular material will be ideal for an application in aerospace. If we can do that, it is a great thing for the experimentalists. They don't have to, run around and do hundreds and thousands of experiments. So, more recently, there is an attempt which is being made to couple this particular, density functional based simulation with high throughput computational screening and combinatorial techniques, which we can call a material informatics, thereby resulting in the fourth paradigm after theory, experiment and simulation in material science. And this fourth paradigm is a confluence of material science and computer science. At this stage of my career, I am trying to enter into this because there is a tremendous dividend which can come. So imagine the youngsters here in the audience. Coming 10 years, I can assure you that those of you who are working in this area, this is something which is going to give you a very, very rich dividend. There is something called materials genome. Many of you know about the Human Genome Project. and today we are entering into what is known as the Materials Genome Project. We start with the quantum chemical and quantum mechanical tools, and then implement the accelerated algorithm, fast data generation, and finally the machine learning protocol for materials discovery. So it's a combination of high throughput computational database using high performance computing with machine learning approach. So I do not want to go into the details because it is basically whatever is written in the red you see. Material scientists have begun to explore data mining ideas for discovery in materials ranging from photovoltaic to thermoelectric to catalysts. Large-scale computations based on well-established physical laws, classical, quantum, and statistical have resulted in a huge computational database activity for designing novel materials and tailored properties. And all these have got a combination of accuracy, robustness, and environmental effects. So this is an example where all the different kinds of ternary semiconductors which are used for the purpose of of the harnessing the solar energy. Remember, these are not experimental data. These are solar spectrum, and these are all the materials. You see, these have been done by using the DFT based data, and we are trying to analyze this. So we are today working on 2D materials, two-dimensional materials, which I already told you. I do not have time to go into this. Now we are in fact going, this 2D material is a new paradigm which is coming out, the graphenes, the silicines, the transition metal dichalcogenide, and many others. So in fact, a whole lot of properties of interest in the 2D material zoo are coming into picture, and we are working on this particularly from the point of view of energy materials, namely photovoltaic and photocatalysis. So 2D materials is a new paradigm which is coming out, and today we can say that a stage is coming thanks to the sophisticated synthesis techniques like molecular beam epitaxy or metal organic chemical vapor deposition, when you can order a 2D material with a desired set of properties and you get it. So the most exciting new material in the 2D diaspora may yet to appear in the horizon. So Shakespeare had written to be or not to be, and I think today we are to be or not to be. So computational material science is a fast growing field, accuracy, tunability, and predictive power. Okay, we can do all these things: microscopic understanding of complex materials and phenomena, design novel materials, quantum mechanical description of interatomic atoms, and availability of enhanced computer power is of course at the root of all this. So today we can simulate as well as predict using DFT based tools materials with varying physical properties, metastable systems, artificial structure, functionally graded materials, materials under extreme physical conditions such as high pressure, high temperature, high magnetic field, etc. 2D materials like graphene and beyond is opening up a completely new canvas. And finally, I told you about the high throughput data generation using high performance computing and machine learning. With that, I stop. Thank you very much for your attention, and I have to acknowledge my students in the material simulation laboratory in IACS. So many of them are presently working, and some of them are. Saurabh is in Vanderbilt University, United States. Sashoto is in IIT Delhi as a young professor. Amrita is in NPL Delhi. Abdul Wasi is in NUS Singapore, and these are the students who are currently about to finish, or some of them are in the process. And I must acknowledge fruitful discussion and collaboration with Chiranjeev Majumdar of BIRC, Devjani Karmakar of BIRC. By the way, I was in BIRC for more than 2 decades, so I continue my collaboration with my young colleagues in BIRC. Rajiv Bhattabbal, who is right now in Weizmann Institute. Ranjit Thapa, I have put it in red because Ranjit Thapa belongs to SRM, who is one of the active organizers of this big mega event. So I am having a very strong collaboration with Ranjit. He may not be here in the audience, but I would like to acknowledge Professor B.N. Deb of ISCS Kolkata, Professor Yoshiyuki Kawazoe of Tohoku University, and financial support from Department of Atomic Energy very generously, and the supercomputer that I use in Japan. So that is where I would like to stop. Thank you.